So welcome to everybody. And this is the March session of the SIFS Young Seminar Series. Today we have, as usual, two speakers. We have Francesco Mori and Giorgio Nicoletti. We will start with Francesco Mori. Let me say a few words about him. Francesco graduated in physics of complex system at Politecnico di Torino, but during his master thesis he's also studied at SISA, ICTP and Orsay. He is now doing his PhD at Orsay, where he works on extreme value theory with Satya Majumdar. So please, Francesco.
Thanks a lot for the invitation. I will just share my screen. Right. Can you see my screen?
Yes, we see your screen.
Right. So today we talk about resetting in stochastic optimal control. This is a joint work with another PhD student in my group, Benjamin De Bruyne. And this is, first of all, an overview of my talk. I will start with a general introduction to optimal control theory and the Hamilton-Jacobi-Bellman equation, which is a framework in optimal control theory. Then I will talk about something different, which is stochastic resetting, which is a very popular topic in non-equilibrium statistical physics. And then I will connect these two different topics, so optimal control and stochastic resetting, and I will explain how to use restarts, so resetting to optimally control different systems. And I will introduce this new framework that we developed with Benjamin on, which we call resetting Hamilton-Jacobi-Bellman equation. So first of all, optimal control is a mathematical framework that allows to optimally drive a dynamical system. It has applications in different fields, from finance to artificial intelligence. For instance, in finance, you can imagine that you want to optimally manage a financial portfolio by buying and selling assets in order to maximize the gain. And in the context of robotics, you may want to your robot to perform a given task. You want to do this in an optimal way. Let's start with the mathematical description. So I will consider a system whose state is described by some dynamical variable, which I call x of t, t is time, which evolves according to some, first of all, to some deterministic law of evolution, which is this simple differential equation. This could describe, for instance, the law of offer and demand in the financial market, or the Newton's law for a robot moving around. But in general, it happens that you may not have a full mathematical description of your system, and you may want to introduce some source of noise to model this missing information. So I also consider a random term in my differential equation. So d in this case is some positive constant, which it's usually called the diffusion constant, and eta is Gaussian white noise. So at each time, eta is a Gaussian variables, and it's uncorrelated at different times, and it has zero mean. Finally, as I said, we want to control this system. So we will consider also an additional term for this equation, which is the external control, u, which is a function of the position and of time, which we can tune as we wish to control the system. So in general, we will have some goal. For instance, in finance, we want to maximize our gain. And this goal is described by the reward function, this capital R, which is again a function of the position of the state of the system X and of time t. But also in controlling the system, we will typically have to pay some price. So again, in the example of finance, you will have to pay some fee for each transaction. And in this case, I will consider simply a quadratic cost related to, so the more I want to control the system, the more I will pay. And our goal is to maximize the payoff. That is the difference between the reward and the cost. So if I consider the evolution of my system during a time window from time t to time tf, the integrated payoff is given by this formula. So it's the difference between the reward and the cost, and then I integrate over different times. However, this will be in general a random variable because the trajectory x of t or x of tau in this case of the system is evolving randomly. And so this is a quantity which will fluctuate from realization to realization of the system, and so I will just consider the average value. And so I put this subscript x naught to indicate that initially assume that the system at time t is in position x naught, and then I want to optimally drive the system up to the final time tf. So overall, I have the expected payoff, which is a function of the initial position of the system x naught and the initial time, which is t, but it is also a functional of the full control policy u of x and t. So what I have to do is that I have to decide my control policy. So just to say, if the system is at position x at time t, I will use this control u of x and t, and this will give me an expected payoff. The question is then, what is the optimal way of controlling the system? So what is the optimal control U star that maximizes this expected payoff? And also I would like to know what is the value of the optimal payoff, which I call J of x naught and t. So just to be clear, J of x naught and t is the expected payoff that I will get starting from position x naught at time t, and from that point onward, optimally controlling the system with the optimal control policy U star. So this in general is a complex functional optimization problem because I have to optimize a very complicated functional of U. However, Bellman and collaborators starting in the 50s developed a very nice framework known as dynamic programming that allows to solve this problem. And in particular, they developed this differential equation, which is now known as Hamilton-Jacobi-Bellman equation, which allows, first of all, to compute the optimal payoff, which is this function j of x and t, solving this differential equation, which depends on the different parameters. So depends on the reward function r and depends on the external force F. Once we solve this differential equation and we get the optimal payoff as a function of x and t, we can also get from this the optimal control policy just by taking the gradient of the function j. So you can understand this because the optimal control U star is driving the system in the direction in which j is increasing the most. So it is driving the system in the direction in which the payoff is increasing the most. So first, you have to solve the differential equation, and then from the solution of the differential equation, you can get the best possible strategy. Let's give a simple example. So let's just set the deterministic part of the dynamics f to 0. So we just have the random part. So this is just a Brownian motion. And in addition, we have the control term that we can tune as we wish. And in this case, I consider the following reward function. So first of all, there is a delta function in time centered at time 1. So the reward will only be present at time 1. And the x dependence states that basically the reward is maximal if the position x is equal to 1. So what you want to do is that you want to drive the system as close as possible to x equal to 1 at the time t equal to 1. So in this little animation, you have the evolution of the system in the vertical axis as a function of time in the horizontal axis. So the goal is to reach this target, which is this red dot, at time t equal to 1, driving the system with this external drift u. So in this case, this problem is exactly solvable, and the optimal control is given by this simple formula, and is represented in the animation by this black arrow, which is either pushing down or up the system to the target. So you can understand this simple formula because the closer you are to the, the further away you are from the target, the bigger the strength of the drift you have to put. And also when the time is closer to the final time, which is in this case 1, the bigger the strength of the control. And this is the optimal strategy in this case. So up to now, we have seen different control strategies which were local and continuous in time. However, in several situations, local and continuous control is not possible, and one needs to apply a global change to the system. So one example is the COVID-19 crisis, during which the main strategies that governments put in place were lockdown, national and regional lockdowns. So what a lockdown did is that it reduced the mobility of a country to a very low level, and this is a kind of global change. Another example of global changes is the case of component replacement in industrial machines. So you can imagine that you have a big complicated industrial machine which is made of many components, and you want to, from time to time, to assess the quality of a given component. So the quality of this component will typically degrade with time, and at some point it may break. So what you want to do is that you want to replace the component before it breaks, but you don't want to replace it too soon because you have to pay the new component. So you have to find the optimal trade-off between replacing the component too soon and letting the machine break. So in both these cases, the optimal strategy or the action you can take on the system is bringing the system back to some known location, or is restarting the system from some known location. So another example in which restarting is useful is when you have a bug in your computer, and typically what you do is that you just restart the computer. So all these different policies to deal with complicated system can be described within the common framework of stochastic resetting, which has become very popular in the context of stochastic processes. So in the basic setting, you can describe stochastic resetting as follows. You consider a dynamical system, x of t, as the one we described before, which is evolving freely according to its own dynamics, which can be deterministic or stochastic, during a certain time interval. In this figure is tau t1. At the end of the interval, the process is reset to its original position. In this case, the position is x equal to 0. And the last ingredient is that the duration of these intervals of revolution are random and are with a given distribution. So stochastic resetting was introduced in 2011 by Evans and Majumdar, and today there are many people working on the topic. The simplest possible case is a diffusion with a constant resetting rate. So which we can describe in the following way. So in a small time interval dt, in one dimension, the position of the system is evolved in the following way. So with probability r times dt, where r is the resetting rate, the system is reset to the starting position, to 0. With the complementary probability, the system is let free to evolve, as a Brownian motion in this case. So there are very interesting features of stochastic resetting. The first feature is that in the case r equal to 0, so for Brownian motion without resetting, the probability distribution of the system as a function of time will always depend on time, even for late times. So there is no stationary state. On the other hand, when you switch on the resetting rate, there is for late times a stationary state, which turns out to be a non-equilibrium stationary state. So resetting is widely used to study non-equilibrium features of stationary states. Another interesting aspect of stochastic resetting is related to the mean first passage time. So for a generic stochastic process starting from 0, you can study the first passage time to a given level L, this green line. So this time, which I call in this figure TF, is a random variable. And in the case of Brownian motion without resetting, so when the resetting rate is equal to 0, the average value of the first passage time is actually diverging, it's infinite. On the other hand, when you switch on the resetting rate, this average value becomes finite, and there is actually an optimal value of the resetting rate R, in which for which the mean first passage time is actually minimized. And this is why stochastic resetting is also widely studied in the context of search processes. So what we wanted to do is, so up to now we have considered a constant resetting rate, but what we wanted to do is to ask if we can find the optimal strategy, making the resetting rate R depend on the position of the system and on time. We wanted to find the optimal strategy to drive, to do some task, so to control the system. So what we did, first of all, is to go back to the dynamics that I described at the beginning and to replace the external control with a resetting rate, which is position and time dependent. So once again, the evolution of the system is the following. So with probability R times dt, dt is a small time interval, the system is reset to the origin. On the other hand, with the complementary probability, you let the system free to evolve. And then you can consider again a reward function, so you want to do some task, and in this case you consider also a cost for each resetting event, which I call C of x and t. And again, as before, you want to maximize the difference between the reward and the cost, which I call the payoff, which is very similar to what I showed before, but in this case we just consider a cost which is linear in the resetting rate. And we average over all possible trajectories. And again, the expected payoff, so the average payoff starting from position x0 at time t, is a functional of the resetting policy, R of x and t. And what we want to do is to find the optimal resetting rate, R star, that maximizes this expected payoff. And as before, we want also to know, if we use the optimal resetting policy, what is the expected payoff? So what is the optimal payoff? And this, as before, is in principle a complex functional optimization problem. So I will start with a simple example. In this case, the reward function is the following. So basically, you will get a reward alpha if you arrive at position x equal to 1 at time t equal to 1. So you want to, in this figure, you want again to reach exactly this target, this red dot. If you reach the target, you get a reward alpha. On the other hand, each time you reset, you will pay a cost, which is constant in this case, and it's called C. Let's consider, before going into the details, let's consider different limits. So when the reward alpha is much less than the cost C, it's never convenient to reset. This is clear, because even if you reset once, you will pay more than the reward you can eventually get. So the optimal strategy is never to reset. On the other hand, when alpha is much bigger than C, so when the reward is much bigger than the cost, the optimal strategy is to reset as soon as you get too far from the target. So you basically ignore the cost of resetting and you reset as soon as you want. But the question is, what happens in between? So when alpha is of the same order as C, what is the optimal resetting strategy? So this is our main result, and to answer this question, we derived a general framework to describe this kind of resetting policy and to find the optimal resetting strategy, which we call the resetting Hamilton-Jacobi-Bellman equation. And the first result is that the optimal resetting policy is the following. So I recall that R times dt is the probability of resetting in a small time interval dt, which turns out to be either 0 or 1. It is 0 if the system belongs to a given domain omega of t, which I call the domain of revolution. So if the system belongs to omega of t, you let the system evolve freely. And it is 1 as soon as the system attempts to go out of this domain. So if the system wants to go out of this domain, you immediately reset it to the origin. So this kind of strategies where the control is either on or off, it's usually called the bang-bang in the control theory literature. This domain omega is then defined as follows. So the free evolution domain is defined as follows. So I recall that J is the optimal payoff that you will get starting from position X at time t. And the domain omega is the domain in which you don't reset the system. So you can understand this as follows. So if the expected payoff where you are, so at position X at time t, is bigger than what you would get after a resetting, which is the optimal payoff starting from 0 at time t minus the cost of resetting, you shouldn't reset, and you should reset otherwise. So this is very clear. On the other hand, we need also to describe the evolution of the optimal payoff, J of X and T, which is given by this differential equation. The only catch is that the domain of definition of the differential equation for the expected payoff is the domain omega itself. So we have that the domain omega is defined, it depends on the solution of the differential equation, and that the domain of definition of the differential equation is the domain omega itself. So these kind of problems are usually called moving boundary problems, and in general one has to solve them numerically. So let's go back to the simple example that I had before. So again, if you get to the target, which is the red dot, you get a reward alpha, and each time you reset, you pay a cost C. So what we said before is these two extreme cases. So when alpha is much less than C, you never reset. So the domain of free evolution omega is just the full real line. On the other hand, when omega is much bigger than C, you reset as soon as you get too far from the target. So the domain omega is just the interval 0, 2, because you are resetting to the origin. So in this animation, the gray part is the complementary of the domain omega, and the white part is the domain omega as a function of time. So using the framework that I showed before, we were able to derive the exact solution to this problem, and we showed that there is actually a critical value of the parameter alpha that we call alpha c, which is equal to square root of 2 pi e times c. And for alpha less than alpha c, the optimal strategy is to never reset. So resetting is never convenient. On the other hand, when alpha is larger than the critical value alpha c, we find a non-trivial domain omega of t. So you can understand this domain as follows. For very early times, so when you still have a lot of time before you have to reach the target, it doesn't make sense to reset yet, because the system is evolving randomly and it could decide on its own to go in the right direction. So you can somehow postpone resetting. So in the region on the left of this figure, you don't reset. On the other hand, when the time is very late, so when you are almost close to you are very close to the final time, it doesn't make sense to reset either, because after resetting, you would be too far from the target and the probability of reaching it would be too small. In between, you have this cone-like shape, which is quite non-trivial, and which in the limit alpha going to infinity will approach this tunnel-like shape that I showed before. So just to summarize, what we did is that we derived a general framework to find the optimal resetting policy. So I showed just one simple example, but this is fully general. This works for very different resetting policies and for a wide class of stochastic dynamical systems. What I showed up to now is just in one dimension, just for simplicity, but you can use this framework in multidimensional systems. And you can also generalize to discrete time system and to more general resetting costs. And what we would like to do for future works is to apply this framework to first passage processes and search processes. For instance, setting the final time, what I called before TF, to be a first passage time. And with this, I thank you for the attention. And if you have any question, feel free to ask.
Thank you very much, Francesco. Are there uh, comments or questions?
I have a question, if it is possible. This is Luca Biferale. Can you hear me?
Yes.
Yes.
Okay.
We hear
okay.
You.
Thank you, Francesco, for the. Maybe you can also see me now. I don't know.
Not yet.
Thank you.
Yes,
thank you, Francesco, for. Thank you for the very nice seminar. I have there is something that is not completely clear to me. I mean, can you explain better what is the interplay between the resetting value and the target? I mean, it seems to me that you have the value x equals 0. I think it's completely arbitrary in principle, right? I mean, you have to decide where to. So do you have also an optimality condition, or I mean, did you study also all these problems as a function of the distance between the resetted value and the target, or is this an interesting question or not?
Yes. I mean, this is important. In this example, I just set the target at 1 just to clear a bit the notation. But it's true that the target position will play a role in the resetting policy, and it actually does. So if you look at what we derived in the paper, we will call this final position XF, and the resetting policy in general will depend on this position. The point is that in general, it's true that the resetting location is somehow arbitrary, but the target location, you can choose it as you want. And what we would like also to do next is to consider the case in where you don't know exactly where the target is. So you have some knowledge of the probability distribution of.
I've lost Francesco. I don't know if you have lost too.
Me too. Francesco? Can you hear me, Luca?
I can hear you, Rosario, but not Francesco.
Not Francesco, me too.
Can you still hear me?
Oh, now
I can hear you.
yes, now we can hear you again. But there was a moment that we were not able to hear you.
Yeah, I saw the connection went away.
So can you finalize your answer, Francesco?
Yes, no, just I was just saying that what we plan to do next is to consider the case where the target location is random, basically. So you don't know in advance where the target is.
Any other question or comments?
Yes, I have a question.
So please, Paolo.
Francesco, you have done some examples with fixed reward and cost function. So I wonder, but this type of approaches to solve the problem, how general they are? I mean, if you modify the reward or the cost function, you have to face a completely different problem, so in some sense you can use what you have found.
I just took the cost and the reward function to be constant to explain this simple example, but the formalism that we derive is fully general. It's completely independent of the particular choice that you make. The equations are exact for any cost and reward function, even if they depend on the position and on time. In general, you will have to integrate the equation numerically, though.
Okay, thank you.
Any other question? Perhaps a short, last short question. I have one brief question. So when you have a stochastic part in your result and in your approach, the stochastic part is always Gaussian, or you could have also other statistical properties? So
up to now, we are able only to do the Gaussian case.
Okay.
But it's if you go, for instance, to a discrete time setting, in which you have some jump, you have like a discrete time random walk with some jump distribution. In that case, we can do any kind of noise, actually. You can choose fat-tailed noise or whatever you want.
Okay. So thank you very much, Francesco.
Thanks a lot.
And